All right, so the question we want to start with in Chapter 2, Section 1 is, what is slope? So from college algebra, we know that slope, m, is equal to f of x2 minus f of x1 all over x2 minus x1, or it is the change in y over the change in x, which is abbreviated as delta y over delta x. So when we're really talking about slope, f of x2 minus f of x1 is the change in the output. And x2 minus x1 is the change in the input. So our slope represents how fast, or the ratio or the proportion of how fast the output is changing with respect to the input. So let's take a look at our first example. So suppose f is a function with input t, and t is in hours, and the output f of t is in miles. What are the units of its slope? Well, if we analyze our slope, it's going to be the change in our output, and our output is miles, so the change in miles divided by the change in hours. In other words, it's going to be miles per hour. So our slope in that case would represent the change in miles over the change in hour, or miles per hour. So this is a velocity, or a speed. So in algebra, we spent a lot of time finding slopes, but we were finding slopes of lines. Well, in calculus, specifically differential calculus, our goal is going to be to expand the idea of slope to nonlinear functions. The piece that's going to help us connect these two things is called the difference quotient. So we'll draw a picture of what the idea of the difference quotient is. So if I have some function named f that looks like this, if I want to try and find its slope, let's say I start at a point x. And if I go up to my graph, it's going to have some corresponding output, f of x. So this would be represented by x comma f of x. And then if I let h be any positive number, so as long as h is bigger than 0, I could find another point over here, x plus h. And if I went to that point on my graph, I would have input x plus h, and its corresponding output would be f of x plus h. So I would get the ordered pair x plus h and f of x plus h. So now we can use our slope formula to determine the slope of the line that connects these two things. So this line right here, we could draw it through these 2 points, is called a secant line. And just FYI, the word secant here has absolutely nothing to do with the secant function from trigonometry. They just happen to have the same name. Well, we do know how to find the slope of a line, so we can just use our slope formula, which is m is equal to y2 minus y1 all over x2 minus x1. So we'll call this point 2, we'll call this point 1. So we would have f of x plus h minus f of x all over x plus h, because that's my x2, minus my x1, which is x. So now if I simplify this up a bit, I get f of x plus h minus f of x all over positive x and negative x, and that gives us h. So we end up with the following formula. So for any positive number h, this is going to give us an approximation of the slope. So now, if we imagine h, the smaller the value of h, the closer these 2 points will be to each other, the better the slope of this line will be as an approximation of this slope. But one thing we notice, we can't let h equal to 0, because if we did, we have an h in the denominator, and it would then have us divide by 0. So, but that's really going to be the big idea that we're going to be studying in Chapter 2 is, well, we know h can't be 0, but what happens as we let h get close to being the number 0? So let's take a look at example 2 and see what we can get. Find the equation of the tangent line to f of x equals sine x plus pi at the point p is 0 comma pi. So going back to our previous example, we talked about a secant line. We're going to need a definition of a tangent line so we can do this problem. So a tangent line touches the graph of a function at exactly one point in a small, we're going to leave that undefined for a minute, open interval. So to help this make sense, let's go back to our picture. So if we were somehow able to make h equal to 0, these 2 points would be the same, and the slope and that line would then only be touching the graph at exactly 1 point in some small interval. So if the graph kept going and came down over here and the tangent line touched it again, that's not going to matter. So the idea is if it came back down over here and intersected really far away from that point, that's not going to matter. So that's why we say in some small interval, so locally, it's only going to touch the graph once. We'll make this more precise as we move on to some other sections, but for right now that gives us a pretty good intuitive idea of what it means. So now we want to find the equation of the tangent line at the point 0 comma pi. So if we put 0 into our equation, we have f of 0 is equal to the sine of 0 plus pi, which equals pi. Oh, we were told that it has the point 0 comma pi. So then we need to calculate another point. So we're going to have f of 0 plus h, which would be the sine of 0 plus h plus pi. So that's going to be sine of h plus pi. So that would be the ordered pair. Well, 0 plus h is just h comma sine of h plus pi. So then now we can find our slope between those 2 points. So m, let's call this point 1, we'll call this point 2, is sine h plus pi minus pi, all divided by h minus 0. So then our pi's reduce out, and we end up with the sine of h divided by h. So that is our slope in our graph for this function. So now, going back to our diagram, our goal is we want to find out what the slope is at 0 in this case. So we're going to let h be a positive number, but we're going to let h get smaller or get close to 0. So let's let h get close, and for right now we're going to leave that as an intuitive understanding. We'll make that precise later on when we start talking about limits, close to the number 0. So let's go ahead and put this into our graphing device. So we go y equals, let's clear this out, and we're going to go with the sine, and our calculator doesn't know x's or h's, so we have to put in x, so sine x alpha y equals to get a fraction over x. And if we were to look at a graph, we get something that looks like this, but let's zoom in a little bit. So let's go zoom and just choose our in. And from eyeballing the graph, what value does that seem to get close to as we get close to the number 0? So if we go trace, we see at 0, since we're dividing by 0, it's undefined, but pretty close to the number 0, we get 0.999952 and so forth. And so remember, we can get close to 0 by going alpha trace, and we could put in some different values. So let's get close to 0. So 0.1 is fairly close to 0, alpha trace. We could get a little bit closer by doing 0.0001. So that's a lot closer. And we get 0.999999983, and we could get even closer by going 0.000001 and pressing enter. And this time my calculator actually gives me the value of 1. And if I kept adding more and more zeros, you'll see that my calculator is finally, even though the value is not 1, what's happening is my calculator is just rounding to the value because it runs out of memory. So this suggests this tells us, no, how should I say that? This implies, yeah, I like implies better, that as h gets close to 0, sine h divided by h gets close to 1. So then we would guess then that the slope is m equals 1, and we found the slope at the point 0, pi. So we could then find the equation of the line that contained these 2 points. So we would have y equals mx plus b, and we plug in our slope, so we get y equals x plus b, and then we plug in our point, we would have pi is equal to 0 plus b, so that gives us that b is equal to pi. So then the equation of the line is y is equal to x plus pi. So this would be the equation of the tangent line. So now let's graph our original function. So our original function f of x was sine x plus pi. So let's grab our graphing calculator. And if we just put in sine of x plus pi, and then we're going to graph our tangent line, which is x plus pi. I'm going to need to adjust our window up a little bit. So window, let's make our y min 0 and make our x or our y max 5. And if we do that, we see there's our sine function. And then we see our tangent line comes in and touches our graph. And then takes off. Our graph curves away. And so at this point, at 0, pi, so this point right here, we see that our slope of the sine function appears to be about 1. So a couple of things we need to mention. The average rate of change is the slope of the secant line. The instantaneous rate of change is the slope of the tangent line. So if you're ever asked about an average rate of change, it's asking you to find the slope of a secant line. And remember, a secant line is a line that just goes through 2 points on the graph of the function x. Whereas the tangent line is like what we have here, where it touches the graph exactly 1 time, and then at that point it represents the instantaneous rate of change. All right, so So the table below shows the distance d in miles traveled by a runner after t minutes. And then we want to determine the average rate of change on each of the following intervals. So when we look at our table, we need to be careful when we're talking about each of these. So there's two ways that we can interpret the data in this table. And what I mean by that is we have distance in miles and we have traveled by a runner after t minutes. So if we have the change in distance over the change in time, this is going to be miles divided by minutes, or miles per minute. We could also have it this way: the change in time over the change in distance. Well, that's going to be minutes per mile. So depending on which slope we're talking about, both of these are useful statistics. One of them is, well, how many miles are you running every minute? And the other one is, how many minutes does it take you to run 1 mile, right? So depending on which way we order the ordered pairs, we're going to get different slopes. And in this physical situation, both of those have interpretations and both of them can be useful. So now let's take a look at A in our example. So when we're given this right here, what's implied, but not given in words, but implied symbolically, is that 7 and 13 here are going to be inputs. Both of these are inputs. So this means I'm going to input 7 and I am going to input 13. And if I go look at my table, do I have values for 7 and 13 in the time row? No. So then these must be distances. So if the distances are the inputs, then the times are going to be the outputs. And remember, our slope is always outputs divided by inputs. So what this is asking us to do is find the average rate of change. Well, that's just a slope. So if I find my inputs of 7 and my input of 13, I'm going to end up with the following. So 72.5 minus 169.8 divided by 7 take away 13. So then if I simplify that up by just putting it into my calculator, so alpha y equals, enter gives me a fraction, 72.5 minus 169.8 all over 7 take away 13. I hit enter and I get, rounding to the nearest hundredth, about 16.22. So now if I keep doing this, and remember in this case, since we're having our distance or our time divided by distance. This is how many minutes per mile, and in this case, that would be the average rate of change. So in this race, the person from mile 7 to mile 13 averaged 16.22 minutes per mile. All right, so let's take a look at B. B has the interval 9 and 13. So then our slope M, this time we look at 9, we're going to have 99.6 minus 169.8 all over 9 minus 13, and we put that into our calculator. We're going to get 99.6, take away 169.8 over 9 minus 13, and we get 40 point, something's wrong. Oh, I'm missing a 99. There we go. I had a typo in the top. I'm like, that's a really, really, really slow mile. So 99.6 should have been the correct number. All right, and we get it 17.55. And we keep going. Our next interval is 11 to 13. So we have M, and we look up at 11. This time we get 132.3 minus 169.8 all over 11 minus 13. Let's see if I can type it into my calculator correctly this time. So 132.3 minus 169.8 all over 11 minus 13. Press enter, and we get 18.75. And then our last one is from 12 to 13. So we do our slope here. We go look at 12, and we get 150.1 minus 169.8 all over 12 minus 13. And in this case, we're going to get 19.7. So what does that tell us? So remember, our units were minutes per mile. So their average pace from mile 7 to mile 13 was 16.22 minutes per mile. From 9 to 13, it was 17.55. From 11 to 13, it was 18.75. And from 12 to 13, it was 19.7. So that means the further they go in the race, it appears that their average rate is slowing. So it's taking them longer to run each mile the further they are in the race. So towards the end, it looks like they got really tired running this half marathon, because when they finished at 13.1, it had taken 173.3 minutes. So that gives us the average rate of change on each of those intervals. All right, so let's answer the last part of this question. It says, use the previous calculations to estimate the velocity, or the instantaneous velocity, at, that should be D equals 13. So at mile 13, we want to come up with an instantaneous velocity. Well, we have the average rate of change on 12:13 is this, so 19.7. Even though it wasn't asked, we could find, well, what is the average rate of change on 13 to 13.1? So if we did that, at 13, we know we had 169.8 minus 13.1 is 173.3. all over 169 paired with 13 minus 13.1. If we grab our calculator and we put this one in, we have 169.8 minus 173.3 all over 13 minus 13.1. We hit enter, and this time we get a huge number. We get 35. So that says for that last tenth of a mile, what happened? They really slowed down. So this actually gives us some information. So this gives us a lower bound for their instantaneous rate of velocity, and this gives us an upper bound. So we know that it's less than 35, and we know that it's bigger than 19.7. We don't know what it is based on the data that we have in this table, but we know it has to be somewhere in between these two things. So one way to get a better approximation would be to average these two things. So we could take 19.7 plus 35 over 2 all over 2 to give us 27.45. Which would be one way to do it, but since the lengths of these intervals are not equal, a weighted average might be better. So we can create the weighted average by doing 19.7 times the length of its interval plus 35 times the length of its interval divided by 1, which was the length of that interval, plus 0.1. And if we do this approximation on our calculator for our weighted average, we have 19.7 times 1 plus 35.2 times 0.1 all over 1 plus 0.1, and we get 21.11, and that's our weighted average. So this is just a regular average, and this is a weighted average. And so a weighted average is like when you calculate a GPA or something, where not all classes are the same number of credits, so you get a different weight when you do that. And recall, to calculate a weighted average, you take the value times its weight plus the value times its weight, and then you divide by, instead of the number of things, the values of the weights, the sum of the values of the weights. And so then either way, they're both a better approximation than just either of the two numbers by themselves. All right.